Hai, Assalamualaikum warahmatullahi taala wabarakatuh. My name is Muhammad Firdaus bin Muhammad Fauzi. My metric number is B0821103663. Okay, I'm from 2 BEI S1/1. Okay, today I will discuss about past year question, subject BEEE 2364, year 2019 to 2020. 2020, question number 4. Okay, question 4. A. Table 4A show the summary of the test waveform for evaluating steady state error of position control system. This is the table. Step, ramp, and parabolic input. We must fulfill the waveform, time function, and Laplace transform. From this note, steady state error is defined as the difference between the input command and the output of the system in the limit as time goes to the infinity. In example, when the response has reached steady state, the steady state error will depend on the type of input, step, ramp, and parabolic, as well as the system type 0, 1, or 2. Note, steady state error analysis is only useful for stable system. You should always check the system for stability become performance steady state error analysis. Many of the techniques that we present will give an answer even if the error does not reach a finite steady state value. We're going to the solution. This is the answer. This is the waveform for step, waveform for ramp, and waveform for parabolic. When the time function is 1, when this is after we convert into Laplace transform, it's become 1 over s. Time function t become 1 over s squared, and 1 over 2 t squared become 1 over s cubed. Okay, next question. Determine the static error constant of Kp, Kv, and Ka and steady state error for input Rt equals 6t minus 5 times ut, given the transfer function of the system. This is the transfer function. Add marks. To answer this question, you must know about the static error constant and system types. The parameter that can be used as steady state error performance specification for unit negative feedback system are called static error constant. The three of these Kp, Kv, and Ka stand for position, velocity, and acceleration error constant. Once you have the proper static error constant, you can find steady state error ESS. The expression for ESS for the case of unity feedback system, namely step input, ramp, and parabolic. Step input equal to ut, ramp input equal to t times ut, parabolic input equal to 0.5 or 1 over 2 times t squared ut. The three terms in the denominator that are taken to the limit determine ESS. These are the static error constant. Note that the value of ESS decreases as the static error constant increases. The static error constant are found from the following formula. This is the formula Kp, Kv, and Ka, but we straightforward to the solution. This is the formula for Kp, limit s approach to 0, GSHS. This one formula for Kv equal to limit s approach to 0 s GSHS, and Ka limit s approach to 0 s squared GSHS. So from the input Rt equal to the previous the question, Rt equal to 60 minus 5. So the minus 5 Rt1, this one Rt2, Rt1 for negative 5 and Rt2 for 60. When Rt1 equal to negative 5 ut, when we convert into the Laplace transform, is become negative 5 over s. And 6t ut, we convert into Laplace transform, become 6 over s squared. This is the equation for input signal that I arranged by my own understanding. It's become negative 5 over s plus 6 over s squared. This negative 5 over s is step input signal, and 6 over s squared is ramp input signal. So we can find Kp, limit s approach to 0, GSHS, Kp equal to limit, then we input the transfer function given. So 5 is we take from here, and s, there is s below, so we times to the transfer function. This one, negative 5 over s times with the transfer function. Then we got the infinity, then we can find the steady state error. Steady state error formula is 1 over the exactly formula 1 over 1 plus Kp. So we got the variable constant value is 5, then we put 5, then become 0. This is how I calculate the value for Kv. ESS also become 0, Kv become infinity, Kp become infinity, and Kp become 1, and steady state error become 1. So we can conclude that steady state error equal to steady state error 1, steady state error 2 plus steady state error 3, 0, 0 plus 1. Yes, the steady state error is 1. This is solution for question 4b. So we go into the next question. Consider a system with a transfer function below. This is the transfer function. And determine natural frequency. Natural frequency is omega n. Damping ratio is zeta. Delay time Td. Rise time Tr. Peak time Tp. Maximum overshoot MP percent MP. Percentage overshoot percent OS. Settling time 42%, settling time for 5%. Okay, this is the article that I got. The article show about overdam, article dam, critically dam, underdam, and undam. In these four things, we can understand by their zeta bigger than 1. When the zeta bigger than 1, it's underdam. When the zeta equal to 1, it's critically damped. When the zeta below than 1, it's underdamped, and when the zeta equal to 0, it's undamped. Okay, this is the formula that I got from my notes. Damped natural frequency omega d equal to, this is one the formula. Okay, we straightforward to the solution. Natural frequency omega square n equal to 106. And then we omega n equal to square root of 106. We convert to the right, from left to the right, squared. Then become 10.3. Damping ratio to zeta omega n equal to 18. Zeta equal to 18 over 2 omega n. Omega n is damping ratio, is natural frequency from the up here. So we convert 2 times 10.3, 18 over 2 times 10.3, then we got 0.874. Okay, for delay time, Td 1 plus 0.7 zeta over natural frequency. 1 plus 0.7 damping ratio over natural frequency. So we have natural frequency, we have damping ratio, then we just convert 1 plus 0.7 times 0.874 over 10.3, then we got 0.1 second, 0.16 second. For number 4, rise time, formula for rise time is 2.16 damping times to damping ratio plus 0.6 over natural frequency. So 2.1c, this is we got 0.24 second peak time pi over natural frequency set 1 minus damping ratio squared. You must have set this here, then we can just dash set and square. Then we got 1.29 second. Maximum overshoot percent MP equal to exponent the power of negative damping ratio times pi over set 1 minus damping ratio squared, then times to 100%. Then we got 0.35% percentage overshoot, exponent negative damping ratio times with natural frequency over WD. WD is also natural frequency times 100%. How to find WD is down here. WD equal to Wn set 1 minus damping ratio square, then we got 5, so we convert into the formula back. Percent overshoot equal to exponent times the power of 0.874, which is the damping ratio, times to 10 over 3, which is the natural frequency for Wn, over 5 is WD that we got here. Don't forget to divide by pi and times to 100, then we got 0.35%. Settling time for 2% from final value Ts equal to 4 over damping ratio times natural frequency. So we got 0.44 second. Settling time for 5% from final value Ts equal to 3 over damping ratio time to natural frequency Wn. Then we got 0.33 second. Okay, this is how we solve the problem when we have a transfer function. Then they need us to find natural damping ratio, delay time, rise time. We must find step by step to complete the question. Okay, that's all for me. If you have anything to ask, we can go into my link to go through to my PDF. That's all for me. Thank you.